Quantum computing is an exciting and rapidly evolving field that has the potential to revolutionize the way we process information. Traditional computers, known as classical computers, use bits to store and manipulate data. These bits can represent either a 0 or a 1. In contrast, quantum computers use bits, simultaneously representing 0, 1, or a superposition of both states. This fundamental difference in how information is stored and processed opens up a new realm of possibilities for solving complex problems. What are bits? A qubit is the basic unit of quantum information. It is analogous to a classical bit but can exist in a state that is a combination of 0 and 1 simultaneously, thanks to a property called superposition. This superposition allows quantum computers to perform parallel computations, leading to exponentially faster processing speeds for specific tasks. Qubits can be realized using various physical systems, such as trapped ions, superconducting circuits, or topological states of matter. Superposition and entanglement. Superposition is a fundamental concept in quantum mechanics that enables bits to exist in multiple states at the same time. For example, a qubit can be in a state that is simultaneously 0 and 1. This lets quantum computers perform multiple calculations simultaneously, dramatically increasing their computational power. Entanglement is another crucial property of quantum systems. When qubits become entangled, the state of one qubit becomes linked to another qubit, regardless of the distance between them. This phenomenon allows quantum computers to simultaneously perform operations on multiple qubits, leading to even greater computational capabilities. Quantum gates and algorithms. Quantum gates are the building blocks of quantum circuits and are analogous to classical logic gates. They allow operations to be performed on qubits, such as changing their state or creating entanglement. Quantum algorithms, such as Shor's and Grover's algorithms, take advantage of the unique properties of qubits to solve particular problems exponentially faster than classical algorithms. For example, Shor's algorithm can factor large numbers efficiently, which has significant implications for cryptography. Before we continue, please hit the subscribe button below to support this channel. Moving on to the applications of quantum computing. Quantum computing has the potential to revolutionize numerous fields. Some potential applications include 1. Optimization. Quantum computers can efficiently solve optimization problems, improving resource allocation, logistics planning, and portfolio optimization. 2. Simulation. Quantum computers can simulate complex quantum systems, enabling advancements in materials science, drug discovery, and understanding fundamental physical phenomena. 3. Cryptography. Quantum computers have the potential to break commonly used cryptographic systems, necessitating the development of new encryption algorithms that are resistant to quantum attacks. 4. Machine learning. Quantum machine learning algorithms can process and analyze large datasets more efficiently, leading to artificial intelligence and pattern recognition advancements. Challenges and future directions. Despite the tremendous promise of quantum computing, significant challenges exist. Building stable and scalable qubits, reducing errors, and improving fault tolerance are ongoing research areas. Additionally, quantum computers require extremely low temperatures and precise control, making operating challenging. Nevertheless, researchers and technology companies invest worldwide in quantum computing research and development. Governments and academic institutions are also exploring quantum technologies and their potential impact on various industries. In conclusion, quantum computing represents a paradigm shift in how we process and manipulate information. With their ability to harness the power of qubits, quantum computers have the potential to solve complex problems that are currently intractable for classical computers. While many challenges remain, ongoing research and advancements in quantum technologies continue to push the boundaries of what is possible. The future of quantum computing holds immense potential and exciting possibilities for scientific discoveries, technological advancements, and societal impact. That's all for now. If you have any questions or suggestions or if anything we missed, please don't hesitate to let us know in the comments section below.